Good morning, everyone. Welcome to the presentation of this work at the 10th Brazilian Symposium on Computing Systems Engineering. The work is entitled A Manycore Vision Processor Architecture for Embedded Applications. My name is Yudi. These are the other authors of this work, and we all work in the Automation and Control Group at the University of Brasília, Brazil. The market for image processing and computer vision applications has grown considerably in recent years. This movement has given rise to the need for devices capable not only of capturing images, but also of processing them. Smart cameras are then proposed as equipment with computational power to run complete applications, as we see in the example of a facial recognition system. A smart camera needs to be optimized for the desired applications, and this can be achieved in two main ways. The first one is the exploration of the intrinsic parallelism of image processing and computer vision. And the second one is the integration of image acquisition and processing into dedicated devices. In this work, we explore both fronts simultaneously, with the proposal of an MPSOC to be integrated into the pixel sensor. Ideally, the image sensor should have multiple AD converters, allowing the acquisition of several pixels simultaneously. Each acquisition channel could then be processed in parallel in different tiles. The literature shows several works in this direction. This concept is known as focal plane image processing. Most of this work focus on analog processing with low-level algorithms, mainly for color adjustments and filtering. In our case, we will focus on the processing and integration of memories and communication structures. In previous works, we explored the design space of these architectures, testing several topologies and alternatives, mainly in simulation. For this work, we decided to implement an MPSOC based on network on chip due to the scalability and flexibility offered, but with the drawback of more significant communication delay to access the distributed memories. Therefore, each tile is composed by a processing element, a pixel memory, and a router. We choose to use a device from the Xilinx ZYNQ family, which integrates an ARM processor with reconfigurable logic. The ARM processor is used to program the processing elements and debug the MPSOC using the AXI bus, which is a standard of the ZYNQ family. In this work, the image is sent by the ARM, emulating the operation of a typical image sensor, the pixels being multiplexed to the corresponding tile. All elements have been designed with a focus on image processing and computer vision algorithms. The figure on the left shows 4 regions of the image, each of which is the responsibility of a tile. Depending on the algorithm, pixel exchange is required among the tiles, and the pixel memory and router structures have been tuned for this purpose. The processing element is a minimalist single-cycle processor with only 16 instructions. The current version has only 15 instructions since the division is being emulated into the software. We do not have a compiler yet. This means that all the tests were implemented in assembly language. The implementation has been optimized for FPGA in order to use the DSP and memory blocks available in the hardware. The router has a typical architecture with fixed size messages composed of only one fleet. All bits are transmitted in parallel, following a synchronization handshake and an XY routing algorithm. In the picture, we can see the components of the messages, all focused on the information needed for image processing and computational vision algorithms. When a processing element needs a pixel from another tile, it requests it from the local router, and the message is routed to the desired tile. The destination router requests the pixel from its pixel memory and sends it back to the source router of the request. There is also a FIFO between each pair of routers to prevent network lockout. Pixel memories have been implemented using memory blocks which are available at the FPGA, and they are just multi-port memories. The ARM processor must be able to write and read pixels to emulate the image and debug sensor. The router performs readings only, and the processing element is able of both reading and writing pixels. To validate the architecture, we chose the Harris corner detector algorithm, which can be implemented as shown in the picture. Each processing element was programmed with the same assembly code, which is parameterized by special purpose registers. Each processing block generates an intermediate image, which is also stored in pixel memories. The implemented manycore is fully parameterizable for the image size and the number of pixels per tile. We use a state-of-the-art ZYNQ SoC, the ZCU104, with a fixed image size of 256 per 256 pixels, varying the number of tiles according to the table. When reaching 81 tiles, we achieved the physical limit of our board and continue increasing the number of tiles only in simulation. In this graph, we have the results in frames per second of the manycore implemented from 1 to 81 tiles and simulated from 1 to 400 tiles. It would be possible to continue increasing the number of tiles, but the simulation time was already in several hours for each case. But we can see here the scalability and the throughput, the performance of the architecture. In the table on the left, we can see a comparison of our results with other works that implement the same algorithm, the Harris corner detector. We can see implementations in FPGA, embedded GPUs, MPSOCs, and SIMD processors. Some FPGA implementations are directly implementations of the algorithms. This means that they are not programmable, so they can only run the Harris corner detector. On the other hand, our architecture is fully programmable and can implement virtually any algorithm in the area. The cycles per pixel metrics were used to show that with efficient parallelism exploration, we can achieve high performance. We also implemented the Sobel edge detector, as it is widely found in the literature, thus having another basis for comparison. This graph shows the performance of our architecture in frames per second for the Harris corner detector, the Sobel, and the convolution with 3x3, 5x5, and 7x7 masks for different amounts of tiles. Something fundamental to do in this work is to separate the pixel access time into two parts. One is the local access, using the pixel memory at the same tile, and the other one is the remote access, made through the network on chip to pixels in other tiles. As expected, there is an increasing communication overhead by increasing the number of tiles. as more remote access is required. In this work, we present an architecture of a manycore vision processor, an MPSOC based on NOC developed specifically for image processing and computer vision applications. We were able to show the feasibility and scalability of this type of architecture with its implementation in FPGA. As future work, we propose the integration of an image sensor, a parameterizable library of algorithms in the area, the measurement of power consumption, and the exploitation of larger FPGAs with more physical resources. We are also looking at the adaptation of a compiler or to replace the processing elements by a more common processor, such as say MIPS. This work was financed by the following funding agencies: CNPq, CAPES, and FAPDF. Thanks for your attention.